Okay, everyone, this is Lab 4, the physics of ropes or springs. We have two fundamental principles, Newton's second law, where the main equation is final velocity equals initial velocity plus the net force divided by mass times the change in time. And we can use the final velocity to then predict the final positions using similar equations. And the energy principle, which is the change in energy equals work, which in this case is the kinetic energy plus the potential gravitic energy plus the potential spring energy. And the force and related values, the gravitic force is equal to negative m times gravitic constant times y directional vector j hat, and the spring force is equal to negative spring stiffness times s, which is the magnitude of the stretched spring minus the distance of the relaxed spring times the directional vector L hat, and these are the only two forces acting on the system. And the mass is 0.402 kilograms, the gravitic constant is 9.8 newtons per kilogram, spring stiffness is 6.83 newtons per meter, the relaxed length of the spring is 0.123 meters, initial velocity is 0, and the initial position is negative 0.115, negative 0.625, and 0. The energy equations to find the total energy. Kinetic energy is 1/2 mass times speed squared. The gravitic potential energy is mass times gravitic constant times the y position. And the spring potential energy is equal to 1/2 times spring stiffness times s squared. The system here is the earth, the spring, and the mass. So the kinetic and potential energies should even out to equal 0, as there is no transfer to or from the surroundings of energy. So here's the experimental data. As you see, it goes both oscillates in the left to right and up and down motion. And if we look at the table of values for x and y position, we see the initial time and the initial x and y positions. If we go back, we can now look at the oscillations, both for the left and right and up and down directions. I found that in the x-axis, the oscillation was 1.52, and on the y-axis, the up and down direction, the oscillation was 1.65 seconds. This difference in is present in the experiment and would not be there in an ideal system, but this is probably because of drag force, which would bleed energy out of the system, and possibly it affects the y position more, which is why the oscillations are longer. So in this VPython file, we match the experimental with the theoretical data. All of the values, such as the ball mass and initial position that we provided in the PowerPoint, are put in here, as well as the equations we pointed out earlier. And we have a CSV file with the experimental data points that we can compare them to. And if we run this, and the time goes to 9.307 seconds, if we run this module, you can see that the values stay the same for a large portion of the time at the beginning, but they gradually begin to lose similarities, and this is because of the drag force, as we pointed out earlier, that slowed down the oscillations and is in the y direction more than the x direction. This bleeds energy out of the system and would slow it down, and because the theoretical data doesn't account for this drag force, they begin to lose similarity over time during the video. And as you can see here, the spring force faces upward in the positive y direction and controls the left and right movement of the ball. And the gravitic force is always pointing down in the negative direction and is always facing towards the earth. And the reason it goes up and down is because these forces are constantly changing, where one will be stronger than the other, changing the direction of the ball in the y direction. So here's the VPython file for the energies, both kinetic and potential energies. And all the formulas are provided here, as long as the change in these energies, where the final minus the initial for each of them. And if we run this file, we end up with, over time, the red is gravitic potential energy, the blue is kinetic energy, and the green is spring potential energy. And as you can see, they oscillate just as the spring does, and altogether they end up equaling zero, which is this yellow line, which is the change in energy going through the x-axis. And this shows that energy is conserved in the system and as it has no interactions with the surroundings. The total energy, kinetic, and potential all adds up to zero, which means the energy principle remains true. And I hope you enjoyed the lab, and I'll talk to you next time.